Hello there, and welcome. Glad you're here. Let your shoulders drop. Let your breathing slow. Let the room grow quiet. Because tonight, we are drifting toward the strangest objects in the universe. Black holes. Places where gravity bends so deeply that even light cannot escape. Places where time itself slows and tilts. Places that exist all around us, hiding in the dark spaces between stars. We'll wander gently from the first photo of one ever taken to the giant black hole sleeping at the heart of our own galaxy. From what would happen if you fell in, to what happens long after every star has burned away, from a black hole the size of a marble to one heavier than 66 billion suns. Some of these ideas are so strange that even scientists are still trying to make sense of them. Tonight, you don't need to make sense of anything. You only need to listen and breathe and let the cosmos pass through you. If these calm journeys help you unwind, consider liking and subscribing to the channel. It helps other tired and curious minds find their way here too, one quiet night at a time. Now, let's begin. Imagine watching someone fall toward a black hole. From far away in your spaceship, you can see them clearly. The dark sphere ahead of them grows larger. They fall closer and closer to the edge. But then, something strange happens. They begin to slow. Not because their engines are failing, not because anything is pulling them back. They slow because time itself is bending around the black hole, and from where you sit, every second of theirs takes longer than yours. The closer they get, the slower they fall. Their motion crawls. The light coming from them stretches and reddens. Their voice, if you could hear it, would deepen and fade. They never quite reach the edge. From your view, they hang there forever, painted onto the dark, slowly fading into silence. To you, they never fall in. They simply, gently stay. For thousands of years we imagined them. We drew them, wrote about them, built equations that described them. But no one had ever actually seen one. Then, in April of 2019, that changed. A team of scientists working with telescopes spread across the planet released the first image of a black hole. It was called M87, a giant 6.5 billion times the mass of our Sun, sitting at the heart of a distant galaxy, 55 million light-years away. The picture itself was simple, a glowing orange ring with a deep black circle at its center, light, bending around something that swallowed it whole. It wasn't a sharp photograph. The black hole was so far away that capturing it had taken years of patient work. But the moment that image appeared on screens around the world, an old question was finally answered. Black holes are real. We have seen one. There is a black hole in our own galaxy. Not far away, not theoretical, not somewhere else. Right here at the center of the Milky Way, 4 million times the mass of our Sun. It is called Sagittarius A, and it has been there silently for billions of years. Tonight, as you lie in bed, it is still there, turning slowly, pulling on the stars that orbit it. Most of the time, it sleeps. It feeds rarely, and when it does, it gives off small flares of light we can detect from Earth. But for now, it is silent. A giant in our backyard, hidden behind clouds of dust, waiting in the dark heart of our home. Time near a black hole does not behave the way time behaves anywhere else. If you fell toward one, every clock you carried, your watch, your heartbeat, the soft rhythm of your breath would begin to slow when measured against clocks far away. Your seconds would stretch. Theirs would race. The closer you got, the bigger the gap would grow. This is not a trick of the light. It is not your imagination. Time itself bends near a black hole, the way a heavy stone bends a sheet of cloth pressed beneath it. What it would feel like to fall in. That is a question we will return to later in the soft middle of the night. Some black holes are unimaginably large. Far out in space at the heart of a distant galaxy sits an object called TON 618. It is one of the biggest ever found. 66 billion times the mass of our Sun. That number is so huge it almost loses meaning. So picture it this way. If you took every grain of sand on every beach on Earth and turned each grain into a sun, you would still need many more Earths to match the weight of this one black hole. It is so large that the dark sphere at its center would swallow our entire solar system many times over. And it is only one of countless others, hidden out in the deep. Every black hole has an edge, a boundary drawn invisibly in space that decides what stays and what is allowed to leave. It is called the event horizon, and it is one of the strangest ideas in all of physics. If you cross this edge, even by a single inch, you can never come back. Not by rocket, not by light, not by anything we know of in the universe. The pull is too strong. Every direction beyond it leads inward. The horizon is not a wall you can touch. It is not something you would feel as you crossed. It is simply a line drawn in space-time, marking the place where return becomes impossible. A point of no escape, hiding in plain sight. Once a black hole forms, its edge can only grow. Every star it pulls in, every cloud of gas, every speck of light. Each addition makes the event horizon a little wider, a little larger, a little more. In the basic laws of physics, a black hole's horizon never shrinks, not by any natural process we had ever measured. Once it spread, it stayed. Or so we thought, for many years. Until a man in a wheelchair, working out the math one careful line at a time, discovered something that changed everything. His name was Stephen Hawking. In the early 1970s, while many physicists were still arguing about whether black holes were even real, Hawking was working on something stranger. He was trying to combine two parts of physics, the rules of the very large and the rules of the very small, and apply them to the edges of black holes. What he found surprised everyone, including himself. Black holes, it turned out, are not perfectly black. Their edges glow. Faintly, almost imperceptibly, they leak energy back into space. Tiny particles slip out of the dark, and over time, over almost unimaginable lengths of time, a black hole loses mass. It shrinks, it fades, and eventually, it disappears altogether. A black hole, Hawking showed, is not forever. It is patient, but not eternal. The universe does not let even these strangest of objects last for all of time. We call it Hawking radiation now, a soft glow at the edge of nothing, the slow undoing of everything that fell in. Around a black hole, light does not travel in straight lines. It curves, it bends, it loops back on itself. The closer it passes to the dark center, the more dramatically its path twists. If you stood at the right distance from a black hole, close enough for the bending to be extreme, but far enough to be safe, something remarkable would happen. The light leaving the back of your head would bend around and return to your eyes. You would see the back of your own head glowing softly in front of you. You would see the stars behind you, the rooms behind you, the entire universe behind you, painted in a thin, shimmering ring around the dark. A mirror made of nothing but bent light. A black hole has no surface. You might picture it as a great dark sphere, a planet without light, a hard shell of darkness moving through space. But that is not what it is. If you reached out toward the edge, your hand would not strike anything. There is nothing there to strike. The event horizon is not a wall, not a stone, not even a thin film. It is a place where the rules of motion change, where one direction closes behind you forever. You would feel nothing as you crossed it. Imagine walking across a field at dusk. The light fades. The way back grows uncertain. And then, without warning, you realize you have already passed the place from which you can return. That is what crossing the event horizon would be like. For most of history, we didn't know black holes existed. Even after Einstein's math suggested they could, no one had seen one. Then, in the 1960s, astronomers began detecting strange bursts of X-rays coming from the constellation Cygnus, the Swan. The source was given a simple name, Cygnus X1. Whatever it was, it gave off no visible light, but it pulled at a nearby star, dragging gas off its surface and heating it to millions of degrees. That gas, falling into something invisible, glowed brightly in X-rays. By the early 1970s, physicists were almost certain. The first black hole ever found. A small, dark thing, 6,000 light-years away. It is still there today, still feeding, still hiding. In 1974, two of the most brilliant physicists alive made a strange bet. Stephen Hawking and Kip Thorne, old friends and colleagues, disagreed about Cygnus X1. Thorne believed it was a black hole. Hawking, oddly enough, bet against it. He didn't really doubt it. He bet against it as a kind of insurance. If black holes turned out not to exist, at least he would win something. He lost. By 1990, the evidence was clear. Cygnus X1 was a black hole, and Hawking signed his name in Thorne's office, conceding gracefully. There is a question physicists sometimes ask, mostly for fun. How small would the Earth need to be to become a black hole? The answer is surprising. The Earth would need to be crushed down to the size of a marble. That number, the size at which any object becomes a black hole, is called the Schwarzschild radius. Every object has one. Even you. Your body has a Schwarzschild radius too, far smaller than an atom, far smaller than anything we can measure. The reason none of these things become black holes is simple. Nothing in nature squeezes them down that far. But the math doesn't lie. Hidden inside everything around us is a tiny, theoretical doorway into the dark. Just outside the event horizon, there is another invisible boundary. It is called the photon sphere, and it is one of the strangest places in the universe. At this distance, close to the black hole but not quite at the edge, the pull of gravity is so strong that light itself can be bent into orbit. Photons, the tiny particles that make up light, can circle the black hole in tight, unstable rings. If you could stand on the photon sphere, you would see beams of light looping past you, going around and around, never escaping, never quite being swallowed. These orbits do not last. The slightest disturbance sends the light either falling inward or breaking free. But for a brief moment, light itself becomes a moon, circling the dark. When matter falls toward a black hole, it usually does not fall straight in. It spirals, round and round, faster and faster, like water swirling toward a drain. As it spins, the matter rubs against itself, and the friction heats it to incredible temperatures, tens of millions of degrees, hotter than any star. This swirling, glowing structure is called an accretion disk, and it is what we usually see when we see a black hole. The disk pours out enormous amounts of light: visible light, X-rays, ultraviolet, radio waves. From very far away, the brightest accretion disks can outshine entire galaxies. A halo of bright fire, circling something that gives nothing back. Long ago, billions of years in the past, the universe lit up with strange, distant lights. When astronomers first noticed them in the 1960s, they couldn't make sense of what they were seeing. The lights were as bright as entire galaxies, but they came from points so small they seemed almost like stars. They were given a simple name: quasars. It took years to figure out what they truly were. Quasars are the bright, swirling disks of matter falling into the supermassive black holes at the centers of young galaxies. When a black hole feeds on a great deal of gas at once, its disk shines so brightly that it can outshine all the stars in its galaxy combined. The brightest quasars we have found can be seen across nearly the entire visible universe. Their light, when it reaches us, has been traveling for 10 or 12 billion years. We are looking back in time, watching black holes that were already old when the Earth had not yet formed. To photograph a black hole, you need a telescope larger than any single telescope ever built. A black hole, even a supermassive one, is small compared to the distances between stars. Trying to capture its image is like trying to read a newspaper held up on the moon. No single dish on Earth could do it. So scientists came up with a strange idea. They linked radio telescopes from all around the world: Hawaii, Spain, Antarctica, Chile, Mexico, 8 observatories on 5 continents. By combining their signals at exactly the same moment, they made something extraordinary. A single virtual telescope, the size of the entire planet. They called it the Event Horizon Telescope. And in 2017, they pointed it toward the heart of a galaxy 55 million light-years away. It took 2 years to develop the picture. The data they had collected was enormous, more than 5,000 trillion bytes, far too much to send over the internet. The team had to ship hard drives in boxes by airplane from one continent to another. Then, slowly, carefully, they began to combine the signals. What they were doing had never been done before. They were trying to draw a picture of something that no one had ever drawn from real data. There was no photograph to compare it to. There was only the math, and their hope that the math was right. In April of 2019, they were ready. The image was released on a single morning. It appeared on news sites, on television, on front pages around the planet. Just one picture, a blurry orange ring around a deep black circle. But for the people who had spent years bringing it into being, it was the first time in all of human history that we had looked directly at one of these objects and seen one looking back. The team did not stop with M87. There was another target, much closer to home, the supermassive black hole at the center of our own galaxy, the one we had been calling Sagittarius A. It is much smaller than M87, only 4 million times the mass of our Sun, instead of 6.5 billion. But it is also much closer, only 26,000 light-years away, almost in our backyard. Photographing it should have been easier. It wasn't. The reason is simple. Because Sagittarius A is so much smaller, the gas around it moves much faster. The image, in the time it took to capture, would shift and blur. It was like trying to take a long exposure photo of a child running, instead of a child standing still. It took 3 more years of work, but in May of 2022 the team released a second image. a bright orange ring around a dark center, the same shape as M87, but this one was different. This one was ours. Long before anyone took a picture of it, we knew Sagittarius A was there. For more than 30 years, two teams of astronomers, one in California, one in Germany, quietly watched the very center of our galaxy. They couldn't see the black hole itself. The dust between the stars was too thick, but they could see something else. They could see the stars closest to it. Watching, year after year, as those stars traced impossibly tight orbits around something invisible, something heavy, something dark. By measuring how fast the stars moved and how curved their paths were, the astronomers calculated the mass of whatever sat at the center. The number they kept getting was the same: 4 million suns packed into a space smaller than our solar system. There was only one thing it could be. 3 decades of patient watching, of nights spent under desert skies, of plotting one tiny dot of light at a time across slow, silent years. And in 2020, 2 of those astronomers, Andrea Ghez and Reinhard Genzel, were given the Nobel Prize in Physics for what they had found. They had not seen the black hole. They had simply watched the dance around it until they were sure. Some black holes don't just swallow matter, they throw it back out. Twin beams of charged particles shoot out from the regions just above and below the accretion disk. These jets travel at almost the speed of light. They cut through space in long, straight lines that can stretch for hundreds of thousands of light years. How exactly the jets form is still not fully understood. The twisting magnetic fields around the black hole seem to launch them, turning a small fraction of the infalling matter into outward-bound rivers of light and particles. The jets are so powerful that they can carve enormous bubbles into the gas of their host galaxies. They can shape the way new stars form. They can reach far beyond the galaxy itself, like silent searchlights pointed at nothing. Sometimes, by chance, one of these jets is pointed almost exactly at us. When that happens, the black hole becomes one of the most extreme objects we can see. Astronomers call them blazars, cosmic lighthouses aimed in our direction, sometimes from billions of light years away. The light from a blazar can flicker and brighten on timescales of hours. From across the entire universe, we can watch a black hole flare, then settle, then flare again. Beams of brightness threading the night. Most of the time, supermassive black holes wait. They feed slowly on cool gas slipping in from the disk. But occasionally, something dramatic happens. A star wanders too close. The pull of gravity from a supermassive black hole is so uneven that the side of the star nearest to it is pulled much harder than the far side. The star, instead of falling neatly inward, is stretched. It is torn apart. These events are called tidal disruptions. Astronomers can see them from across the universe. The disrupted star releases a brilliant flare of light as it is shredded, brightening for weeks or months before fading again. Each one is a kind of cosmic obituary. A star that lived for billions of years, ended in a single, slow act of pulling apart. When a star is torn apart by a black hole, what remains of it does not vanish all at once. Half of the star's matter is flung out into space, scattered. The other half is pulled inward, and as it falls, it stretches into something strange, a long, thin ribbon. A stream of stellar material hundreds of thousands of miles long, curving in a wide arc as it spirals down toward the dark. Astronomers call this a tidal disruption stream, the torn star becoming a thread. The stream wraps around the black hole, slowly settling into a new accretion disk. Over months and years, the matter is consumed. The star, no longer a star, is finally swallowed. What remains is a faint, glowing afterthought, a line of light slowly fading where a sun used to be. Most black holes behave consistently. Some feed brightly all the time. Others stay dark and silent year after year. But not all of them are so steady. There is one called V404 Cygni that lives in our own galaxy, 8,000 light-years away. It is a stellar mass black hole paired with a star that orbits it closely. For decades, V404 Cygni does almost nothing. It sleeps. Then, without much warning, it wakes up. The black hole begins to feed, fast and chaotically. Its accretion disk flares to thousands of times its normal brightness. For weeks, it pours out a storm of X-rays and visible light. And then, just as suddenly, it goes silent again. It happened in 1989. It happened again in 2015. And astronomers, telescopes ready, wait for the next time. Far across the universe, at the heart of a giant cluster of galaxies, sits one of the largest black holes we have ever found. It is called Phoenix A. Its galaxy was first noticed in 2010, and the black hole inside it is so enormous that astronomers had trouble accepting their own measurements at first. The estimates vary. Some put it at around 100 billion times the mass of our Sun. The number is uncertain. Measuring black holes this far away is hard, and different methods give different answers. But even at the lower end, Phoenix A is staggering. If you placed it where our solar system is, its event horizon would extend far beyond Pluto, swallowing every planet and comet we know. A single black hole holding more mass than the Milky Way's many billions of stars combined. For most of the universe, the size of a black hole is closely related to the size of its galaxy. Bigger galaxies grow bigger black holes. They develop together over billions of years. But every now and then, a galaxy breaks the rule. There's a galaxy called NG C1277, about 220 million light-years away. It is small, compact, less impressive than our own Milky Way. By the usual rules, the black hole at its center should be modest. It is not. The black hole inside NGC1277 is enormous, roughly 17 billion times the mass of our Sun. For its galaxy's size, it is a stunning anomaly, far too big for the home it lives in. Astronomers are still trying to work out how such a small galaxy ended up with such an oversized heart. Until recently, the closest known black hole to Earth was thought to be thousands of light-years away. Then, in 2022, that changed. A spacecraft called Gaia, mapping the positions of billions of stars, noticed something strange. A bright sun-like star was wobbling, as if tied to something heavy. But there was nothing visible nearby. The something heavy was a black hole. It is called Gaia BH1, and it sits only 1,560 light-years from Earth, by cosmic standards, just down the street. For many years before Gaia BH1 was found, the closest known black hole was a different one. Its name is A0620-00, a name only an astronomer would love. It sits about 3,300 light-years away, paired with a small, dim star. It is a stellar mass black hole. Quiet, mostly, not feeding much, just slowly orbiting its companion in a long, patient dance. Even now, it is still there, closer than most stars in the night sky, hidden in plain view between the constellations. In a galaxy 3.5 billion light-years away, there is something stranger than a single supermassive black hole. There are two. The system is called OJ287. At its center sits a black hole roughly 18 billion times the mass of the Sun, and around it, in a slow, tilted orbit, swings a second, smaller black hole. Only 150 million suns, almost a child by comparison. Every 12 years, the smaller one plunges through the larger one's accretion disk. The collision releases a blinding flare of light, brighter for a brief moment than entire galaxies. We have been watching them dance since the late 1800s, long before we knew what they were. Two black holes locked in a slow gravitational embrace, dipping toward each other across geological time. On the morning of September 14, 2015, an alarm sounded in two laboratories on opposite sides of the United States. The instruments had picked up a faint ripple, a signal so small it would have moved a mirror by less than the width of an atom's center. But the signal was real, and it had arrived at both laboratories within a fraction of a second of each other. For half a century, scientists had been searching for ripples like these. Predicted by Einstein in 1916, but never directly seen. Gravitational waves are tiny disturbances in the fabric of space-time itself, set off by violent cosmic events. This particular ripple had begun its journey 1,300,000,000 years ago. Far away, two enormous black holes had spiraled into each other and merged. The collision had shaken space-time so hard that the wave was still traveling outward all this time later. They named the signal GW 150914, the first gravitational wave ever directly detected, a faint ripple after a billion years of crossing the dark. The two instruments that caught the ripple were called LIGO. The name is short for the Laser Interferometer Gravitational Wave Observatory. Each one is a giant L-shaped tunnel, 4 kilometers long on each arm. Inside, beams of laser light bounce back and forth between mirrors hung in near-perfect stillness. When a gravitational wave passes through, it stretches one arm of the tunnel and squeezes the other, by an amount smaller than a single atom. The lasers measure that stretch. The wave is red. It took decades of work, billions of dollars, and the patience of more than 1,000 scientists to build them. And in their first full month of operation, they caught their first wave. Since then, LIGO has detected dozens more. The universe, it turns out, is full of gentle ripples. Most galaxies have one supermassive black hole at their center, sometimes a second, if they have recently swallowed another galaxy. But the very biggest black holes we have found tend to live in the very biggest galaxies. In a galaxy called Holmberg 15A, about 700 million light-years from Earth, there is one of the largest of all. Its mass is estimated at 40 billion times the mass of our Sun. The galaxy itself is huge, a giant elliptical, the brightest in its cluster, the result of countless mergers. As it grew, by feeding on smaller galaxies, the supermassive at its heart grew along with it. Each merger added a little more mass. Each smaller black hole, drawn in over millions of years, joined the giant. It is a dark monument, built from the wreckage of other galaxies. When you look at a photograph of a black hole, the dark circle in the middle is not actually the event horizon. It is something larger, a trick of light played by gravity itself. The black region is called the black hole's shadow, and it is bigger than the event horizon, usually about 2.5 times wider, because the light passing close to the black hole is bent so severely that it reveals more darkness than the horizon alone would. You are not seeing the edge of the black hole. You are seeing a kind of magnified silhouette, drawn by the curving paths of light around it. This is why, Even though the M87 photograph looks like a simple ring, what you are really seeing is more subtle. Light, bending, distance, deceiving the eye. A shadow larger than the thing that casts it. The accretion disk around a black hole is not smooth. Up close, if you could watch it patiently, you would see a kind of weather inside it. Pockets of gas grow brighter than their surroundings, glowing fiercely for a few hours or a few minutes, then fading. These hot spots flare and dim across the disk, like fires kindling and going out, all on their own. Some are caused by sudden bursts of falling matter. Others are caused by twists in the magnetic fields, when threads of magnetism snap and reform, releasing huge amounts of energy in an instant. Astronomers can sometimes see these hotspots passing in front of the dark center of the black hole. Brief flickers repeating every few minutes, like silent fireworks at the edge of nothing. Earlier, we touched on what it might be like to fall toward a black hole. Now, in the soft middle of the night, let us return to the question. Imagine, this time, that you are the one falling. Not someone you watch from far away, but you yourself, falling toward the dark sphere ahead. From your own point of view, things are not what you expect. You do not slow down. Your clock keeps ticking at its normal speed. You feel no sudden change as you near the edge. The black hole grows in front of you, larger and larger. But the universe around you still seems to behave as it always has. You cross the event horizon. And here is the strangest thing. You do not feel it. There is no jolt, no shudder, no sound, no wall of light. Nothing changes about the air or the metal of your spaceship or the way your hand rests on the seat beside you. You simply cross, without realizing it. The threshold is invisible, even to the one passing through. But there is a catch, a serious one. If the black hole you fall toward is small, a stellar mass black hole, only a few times the mass of our Sun, you will not survive long enough to reach the horizon. The reason is gravity, and how it pulls on different parts of you. Your feet, if they are pointed toward the black hole, are pulled harder than your head. The difference is small at a distance, but it grows quickly as you fall closer. Soon, your feet are being pulled away from the rest of you with a force you cannot resist. You begin to stretch. Slowly at first, then violently. Your body is drawn out into a long, thin shape, like dough being pulled thinner and thinner. This process, in a piece of dark scientific humor, is called spaghettification. For a small black hole, this stretching begins long before you reach the event horizon. You would feel the first uncomfortable pull while still many miles outside. By the time you got close, you would already be undone, pulled apart at the seams cell by cell, atom by atom. Most of you would be torn into a long stream of falling material. None of it would arrive intact at the edge. For a small black hole, the journey ends before it truly begins. But for a much larger black hole, the story changes completely. A supermassive black hole, like Sagittarius A or M87 or TON 618, is so enormous that the difference in pull between your head and your feet, even very near the horizon, is small. You would not be stretched. You would not be torn apart. You would simply fall, calmly, intact, all the way through the edge. You would feel nothing. You would see nothing strange happen to your body. You could look down at your hands and they would still be your hands. You could check your watch and it would still be ticking. You would cross the event horizon, pass the boundary that nothing returns from, and not even know that you had. Only later, deeper inside, would gravity finally grow strong enough to begin tearing you apart. By then, you would already be far past any chance of escape. By then, the spaghettification would simply be the slow, inevitable end. The largest black holes are gentle until they are not. Once you cross the event horizon, the rest of the universe becomes unreachable. No matter how powerful your engines, no matter how loud you shout, no matter how bright a beam of light you point upward, nothing you do, nothing you send will ever reach the outside again. The horizon is a one-way door. Things may enter. Nothing may leave. This is not a matter of distance. It is not even really a matter of speed. It is the geometry of space-time itself, twisted so completely that outward has stopped existing as a possible direction. If you wanted to send a final message to the universe behind you, the time to send it was before you crossed. You did not. While you fall, time does something strange. Earlier, we said that from far away, your clock would seem to slow as you approached the horizon. From your own view, your clock keeps ticking at the normal speed, but the reverse is also true. And even stranger, the universe behind you, from your point of view, begins to race. Look back as you fall, and you see the rest of the cosmos unfolding faster and faster. Stars are born and die in moments. Galaxies twist into shapes you cannot follow. Civilizations rise and end in the blink of an eye. Whole eras of cosmic time pass while you fall a few more miles inward. If you took long enough, you might see the entire history of the universe play out behind you, sped up like a film flickering at impossible speed. Worlds would form, burn, and fade. Suns would gather and scatter. The stars themselves would eventually all go out. And still, you would only be falling. The light from the universe behind you does something else too. It compresses. As you fall closer to the black hole, the path of light from the outside curves more and more. The stars above you, the galaxies behind you, the entire visible cosmos, all of it begins to appear in a smaller and smaller area of your sky. What was once spread across the heavens now collapses into a tightening circle, a kind of shrinking window above your head. If you looked up, you would see the universe gathered into a bright, narrowing disk, with darkness all around it. The cosmos folded into a single, slowly closing eye. A reverse sky, drawing itself shut as you fall. The light in that shrinking circle does not look the way it used to. Because the universe outside is, from your point of view, racing through time, the light it sends you has been sped up too. Its waves have been squeezed shorter. Its colors have shifted toward the blue. The whole compressed sky above you glows with a brilliant, unfamiliar blue-white light. A deep, electric color that does not exist in any normal star or galaxy. It is as if the entire cosmos has been pressed into a single ring of cold fire, hanging just above the dark. Imagine looking up from the bottom of a deep well and seeing not a soft circle of sky, but a brilliant gem of compressed light, blazing in the endless black. That is what falling into a black hole would look like. There is one more strange thing about being inside a black hole. You can no longer move outward. Outside the event horizon, you can choose any direction. Up, down, left, right, forward, back, all are open to you. Even close to the black hole, with all its terrible pull, there is still a way out if your engines are strong enough. But once you cross the horizon, that freedom ends. Inside, every direction you can move is a direction toward the center. There is no path that leads back out. The geometry of space itself has been twisted so that all roads lead inward. You can fight if you want. You can fire your engines as hard as they will go. but the only thing you will manage to do is reach the center sooner. The deepest strangeness, though, is this. Inside the event horizon, the directions of space and time begin to swap. Outside, time always moves forward. You can stand still in space or move through it, but time keeps flowing whether you want it to or not. The future is something you fall into, no matter what. Inside the horizon, that role passes to space. The center of the black hole, the singularity, is no longer a place. It is a moment, a future that you cannot avoid, just as you cannot avoid tomorrow. You do not fall toward the singularity the way you fall toward a hole in the ground. You fall toward it the way you fall toward your next breath. It is not a destination in space. It is a destination in time. You may travel to the right, you may turn left, you may try to climb upward. None of it matters. The singularity arrives anyway, just as the next second always arrives. Forward in time, inside a black hole, simply means inward. What is at the center then? What is the singularity exactly? We do not really know. In the math of general relativity, Einstein's theory of gravity, the singularity is a single point of infinite density. All the mass that ever fell into the black hole is squeezed into a place with no size at all. Zero volume, endless density. But infinite density is not really a physical thing. It is a place where the equations stop making sense, where the numbers, instead of giving an answer, divide by zero and break. Most physicists believe this means the singularity is not literally a point of infinite density. It is, instead, a place where our current physics fails. Beyond it, there must be something. We just don't know what. For a non-rotating black hole, the math points to a single point at the center. But almost no real black hole is perfectly still. Black holes spin, often very fast, and when they spin, the math says the singularity at their center is no longer a point. It is a ring. A perfect circle of impossible density, hidden deep in the dark, turning forever. Some physicists have wondered, in the strangest moments, whether anything could pass through such a ring without touching it. Whether there might be, on the other side, something other than the inside of a black hole. A new universe, perhaps. A new geometry. These are speculations. The math hints, but the math also breaks. We have no way to look. The ring, if it exists at all, sits beyond every camera and every telescope we will ever build. What lies inside, in the deepest places, is one of the great unsolved questions of physics. It is not just that we cannot see. It is that, at the center, our best laws of physics simply stop describing what is there. The equations break. The numbers stretch toward infinity. The familiar rules of the universe softly fail. And so, perhaps the most honest thing to say is this. We do not know what a black hole is all the way down. That mystery, and the strange ideas physicists have invented to try to solve it, is something we will turn to soon. Black holes have another peculiar property, hidden inside the math of relativity. A black hole has only three things you can measure: its mass, how heavy it is, its spin, how fast it rotates, and its electric charge if it has any. That is all. Those three numbers are everything you can know about it from the outside. It does not matter what fell in to make it. Stars, planets, dust, light, ships, books, oceans, songs, every single thing reduces, at the horizon, to the same three numbers. The information is hidden, perhaps lost. Physicists call this the no-hair theorem. The idea that a black hole, no matter how complicated its history, has no remembered features, no surface details, no ornaments. A black hole has no hair. just 3 silent numbers. Sometimes, deep into a question, it is worth stopping for a moment to notice how strange the question is. We have been falling into a black hole in our minds together. We have stretched and folded and crossed an invisible threshold. We have watched the universe outside speed up and squeeze itself into a brilliant point of light. We have followed the math past the edge into a place where space becomes time and time becomes inevitable. And we have arrived, at last, at the center. A point that may not be a point. A place where the rules of nature itself stop holding. What is there? The most honest answer is that no human being knows. The math we have was never built for the inside of a black hole. The closest scientists have gotten is to suggest that something, some deeper layer of physics we have not yet found, must take over where the equations break. Some imagine a new kind of geometry. Some imagine the seed of a new universe. Some imagine a deep stillness, where mass and light and memory all merge into something we have no language for. Tonight, we do not need an answer. We only need the question, and the question is enough to rest on. Long before Einstein, long before the math of relativity, an English clergyman wrote a letter that would, 2 centuries later, turn out to be remarkable. His name was John Michel. The year was 1783, and he was thinking about something simple. If you could keep adding mass to a star, making it heavier and denser, would there come a point where its gravity grew so strong that even light could not escape? His answer was yes. He called these objects dark stars. He thought they would be invisible, black against the black sky. He worked out, roughly, how massive they would have to be. It would be more than 100 years before anyone took the idea seriously. But the first person to imagine a black hole was a country priest, sitting at his desk on a winter night, doing math by candlelight. In 1915, Albert Einstein published his theory of general relativity, a new way of describing gravity, not as a force but as a curving of space and time around heavy objects. The math, even for Einstein, was difficult. But within a few weeks of seeing the equations, a German astronomer named Karl Schwarzschild found a solution. He was 42 years old, and at the time, he was not in a comfortable office. He was a soldier on the Eastern Front of the First World War, calculating artillery trajectories for the German army. In the trenches, between assignments, between the cold and the noise of the front, he worked through Einstein's equations and found something extraordinary. If a star was compact enough, his solution showed, gravity around it would become infinite. Light would not escape. There would be a boundary beyond which the star simply disappeared from the rest of the universe. He sent his work to Einstein, who was astonished. A few months later, Schwarzschild died of an illness contracted at the front. He never saw the field he had opened. Even after Schwarzschild's solution, almost no one believed black holes were real. Einstein himself, the man whose equations had predicted them, doubted they could exist in the actual universe. He thought the math was an interesting curiosity, a strange edge case, something that could not happen in practice, only in equations. In 1939, more than 2 decades after Schwarzschild's work, Einstein wrote a paper trying to show that black holes were impossible. Real stars, he argued, would never collapse far enough. Something would always stop them before they reached the dangerous boundary. He was wrong. The same year, 2 other physicists, Robert Oppenheimer and Hartland Snyder, published a paper showing exactly how a star could collapse into a black hole. The world had bigger things on its mind that year. The paper was almost ignored, For decades, the objects had no good name. Physicists called them frozen stars, or collapsed stars, or completely gravitationally collapsed objects, long phrases that did not stick. Then, in 1967, a physicist named John Wheeler used a simpler term in a public lecture. He called them black holes. The phrase caught on almost overnight. It was vivid, short, easy to remember. By the early 1970s, it was the only name anyone used. A whole field of study, finally given a name that fit. Most black holes are born from the deaths of massive stars. A star, throughout its long life, is balanced between two forces: gravity, pulling everything inward toward the center, and the energy of nuclear fusion at its core, pushing everything outward. For most of a star's life, these two forces are equal. The star is steady. It glows. It burns slowly through its hydrogen, then its helium, then its heavier elements, one fuel after another. But fuel runs out, and when it does, gravity wins. The core, with nothing to hold it up anymore, collapses inward. In a fraction of a second, what was once a region wider than a planet is squeezed into something smaller than a city. And then, smaller still. That is how the densest objects in the universe begin. Not slowly, all at once. When a massive star's core collapses, the collapse releases an enormous amount of energy. The outer layers of the star, suddenly with no support beneath them, fall inward too. They crash against the dense core. They bounce. They explode outward in one of the most violent events in the universe. This is a supernova. For days or weeks, a single dying star can outshine its entire galaxy. Its light reaches across millions of light years. Its outer layers are flung into space at nearly 10% the speed of light. But while all that drama unfolds outside, something else has happened in the very center. The core, the small heart of the star, has not bounced back. It has kept collapsing. If the star was massive enough, the core does not stop until it has become a black hole. But not every massive star ends with a supernova. Some, especially the most massive ones, skip the explosion altogether. The core collapses inward, just as it would for any other dying giant. But this time, gravity is so strong that even the outer layers are pulled in instead of being flung away. Astronomers call this a failed supernova. The star does not blaze. It does not light up the sky. It simply stops shining. One night, the star is there, glowing in the heavens. The next, it is gone. No flash, no farewell, just absence. What used to be a star is now a black hole, sitting where the star used to be, pulling on its surroundings just as the star did, but invisible, without ceremony. Some of the largest stars in the universe vanish from the sky this way. Not every star ends as a black hole. Most stars, including our sun, are too small. When they run out of fuel, their cores collapse only part way. They become white dwarfs, or if they are slightly larger, neutron stars. To make a black hole, a star needs to be at least about 20 times the mass of our sun. That sounds like a lot. But the universe has no shortage. Across the Milky Way alone, there are millions of stars massive enough, and every one of them, eventually, will leave a black hole behind. Black holes are not always born from the death of a single star. Sometimes they are born from the deaths of two stars at once. A neutron star is what is left when a smaller massive star collapses but does not quite become a black hole. It is a city-sized ball of matter, denser than anything else in the natural universe except a black hole itself. Sometimes, two neutron stars are born close together, orbiting each other in a tight pair. For millions of years, they spiral slowly toward one another. Then, in their final moments, they collide. The collision is one of the brightest events in the cosmos, and often, the merged object is too heavy to remain a neutron star. It collapses in an instant into a black hole. A new black hole, born of two stars at the same moment. Not all black holes were born from stars. In the very early universe, within seconds of the Big Bang, conditions were different from anything we see today. Matter and energy were packed together at unimaginable densities. Tiny ripples and pockets of higher density may have existed everywhere. In some of those ripples, the math suggests, the density grew so high that a region of space simply collapsed into a black hole, all on its own. No star needed, no supernova required. These are called primordial black holes that may have formed when the universe was less than a second old. If they exist, they could be of almost any size. Some could be enormous, others could be smaller than an atom. Tiny black holes passing through space, perhaps even through Earth without us noticing. Astronomers have searched for primordial black holes for decades. So far, none have been found. But the universe is large, and the search is far from over. For now, they remain a beautiful possibility. Children of the first instant of time, the earliest black holes formed astonishingly fast. For most of human history, we imagined the early universe as a slow, gentle place, filled mostly with hydrogen and helium, taking its time to assemble galaxies and stars. But recent telescopes looking far back in time have shown us something different. Black holes were already there, fully formed, when the universe was less than 100 million years old. By that time, large, supermassive black holes were already feeding, already lighting up their surroundings. How they grew so big so quickly is one of the great unsolved questions in modern astronomy. There simply was not enough time for ordinary star deaths to build them. Something else, something faster, must have been at work. What that was, no one yet knows. One leading idea is called direct collapse. In the very young universe, before stars had fully formed, enormous clouds of hydrogen moved through space. Most of these clouds, given enough time, would have broken into smaller pieces and condensed into stars. But some, under the right conditions, may not have broken into pieces at all. Instead, the entire cloud, many thousands of times the mass of our Sun, could have collapsed all at once. No fragmentation, no stars, just one enormous gravitational fall. The result would be a black hole, born already huge. Already 100,000 suns, perhaps a million, packed into a single dark seed at the moment of birth. These massive infant black holes, if they truly formed, may have been the seeds from which the supermassive giants of today's universe grew. Another idea is that the supermassive black holes grew from a special generation of stars. Astronomers call them Population 3. They were the very first stars in the universe, formed from clouds of pure hydrogen and helium, before any heavier elements existed at all. Population 3 stars were unlike anything alive in the universe today. They were enormous. Some may have reached hundreds of times the mass of our Sun. Their lives were short, just a few million years, and when they died, some of them collapsed directly into black holes. A galaxy full of these monsters would have left behind a great many black holes, all at once. Over the next billion years, those black holes could have merged, fed, and grown into the supermassive giants we see today. Whether this is what really happened, no one can be sure. But the math fits and the timing is right. Black holes do not form in stillness. When a star collapses to make a black hole, it brings with it whatever motion it had. If the star was rotating, and almost every star does, that rotation is preserved. As the star shrinks, it spins faster and faster, in the same way a figure skater speeds up when she pulls in her arms. By the time the collapse is complete, the new black hole can be spinning at extraordinary speeds. Some are estimated to rotate at more than 90% the speed of light at their event horizons. These are not slow, steady objects. They are giant, dark whirlpools, set spinning in their first moment and never tiring. A black hole inherits the spin of the star that died to make it. There are several different sizes of black holes in the universe, and each has its own story. The smallest are called stellar mass black holes. These are the ones formed from collapsing stars, the kind we have been discussing for many sections now. Their masses range from about 5 times the mass of our Sun up to perhaps 100 suns. Most are toward the smaller end. Stellar mass black holes are by far the most common. There are likely hundreds of millions of them in our galaxy alone, scattered across the disk and halo, mostly invisible. Some of them sit alone in space, moving through the dark. Others are paired with companion stars, the way Cygnus X1 is. A few have been detected. Most remain hidden, simply too small and too dark for us to see. In between the stellar mass black holes and the supermassive ones, there should be a middle group. Intermediate mass black holes. Hundreds, thousands, or tens of thousands of times the mass of our Sun. By every reasonable theory, these should exist. They should be common. They should be the bridge between the small ones and the giants. But somehow, in all our searching, we have barely found any. A whole missing class of objects, hiding somewhere in the universe, or perhaps not existing at all. At the very center of nearly every large galaxy in the universe sits a supermassive black hole. Our own Milky Way has Sagittarius A. The galaxy nearest to us, Andromeda, has one even larger. Every spiral galaxy we have looked at, and every large elliptical galaxy, contains one of these dark giants at its core. Their masses range from a few million suns, like Sagittarius A, up to tens of billions for the largest. How they got there, no one fully knows. But the pattern is unmistakable. A galaxy is not just a collection of stars and gas. It is almost always a galaxy with a giant black hole at its heart. It is one of the deepest patterns in the cosmos. Galaxies and supermassive black holes belong together. Here is one of the strangest facts about black holes. A larger black hole is, paradoxically, less dense than a smaller one. It seems wrong at first. Density usually means how packed something is, and we tend to imagine bigger objects as more compressed, more concentrated. With black holes, the opposite is true. The reason is that the size of a black hole's event horizon grows in proportion to its mass. Double the mass, double the radius. But volume grows as the cube of the radius. So when a black hole gets larger, its volume grows much faster than its mass. Some of the largest supermassive black holes are so spread out that, on average, they are less dense than air, less dense than water, less dense than your own body. A giant of the cosmos, in the right sense, is barely there at all. Beyond the supermassive black holes, there is another class: ultramassive black holes. Objects with more than 10 billion times the mass of our Sun. The very largest may approach 100 billion. They are the heaviest single things ever found in the universe. We have already met a few of them: Ton 618, Phoenix A, the giant at the heart of Holmberg, 15A. Where they came from is still being studied. Most of them sit at the centers of the largest galaxies in the largest clusters. To grow to such sizes, they likely fed for billions of years on incoming gas, on smaller black holes, and on the wreckage of countless mergers. If anything in the universe deserves to be called a true cosmic monster, it is one of these. At the other extreme, there is a possibility that some black holes are unimaginably small. If primordial black holes exist, those formed in the first moments of the universe, they could be of almost any size. Some could be the size of mountains. Some could be the size of basketballs. Some could be smaller than an atom. A black hole the mass of a small mountain, but smaller than a single proton in size, would still pull on its surroundings with terrible strength. It could pass through a planet without anyone noticing. It could orbit a star without ever being seen. If they are real, the universe might be full of them. Microscopic, almost weightless to us, slipping through space without a trace. A whole population of dark, atom-sized seeds left over from the dawn of time. There is a strange feature to thinking about black holes for a long time. The deeper you go, the stranger the questions become. We started with simple things: a dark sphere in space, a boundary nothing can cross. We watched matter fall in. We watched light bend around. We followed a falling traveler all the way through the horizon. But the further we have moved, the more the ground beneath the questions has fallen away. We have arrived at places where space and time swap roles, at points that are not really points, at a center where our equations stop working entirely. Now, in the middle of the night, we begin to ask questions about the questions themselves. What does it mean for information to be lost? What does it mean for a place to have temperature, even when it is dark? What does it mean to say that the inside of a black hole might be a kind of universe of its own? Tonight, none of these questions have neat answers. They are open frontiers, strange edges that physicists have argued about, sometimes happily, for half a century. Let yourself wander among them now, the way you might wander among unfamiliar stars on a clear night. You do not need to know what they are. You only need to look. Earlier, we noted that anything which falls into a black hole seems to be reduced to just three numbers: mass, spin, charge. Everything else, all the detail, all the history, all the differences between a falling rose and a falling river, appears to be lost. Physicists have an unsettling name for this. They call it the information paradox. In the rest of the universe, information is never destroyed. The pattern of atoms in a burning book is, in principle, recoverable from its smoke and ash. Even the smallest details of the past are preserved somewhere, even if we cannot read them. But a black hole appears to break this rule. Things fall in, and their details simply vanish. Most physicists believe the information must somehow still exist, that it is not really destroyed, that it is hidden, encoded somewhere we have not yet learned to look. Where, exactly? That, for now, is one of the great mysteries of physics. Hawking's discovery did something else strange. It showed that black holes have a temperature. This sounds impossible at first. A black hole is dark, cold, nothing escapes its grasp. How can it be said to have a temperature at all? But Hawking's math was clear. The faint glow we now call Hawking radiation behaves exactly the way a warm object's glow behaves. The temperature is incredibly small. For a black hole the mass of our Sun, it would be less than a millionth of a degree above absolute zero. For a supermassive black hole, the temperature is even smaller, but it is not zero. This is one of the deepest clues physicists have. A black hole, despite being defined as a place from which nothing escapes, behaves like an object with warmth, with thermal life of a kind we are only beginning to understand. If a black hole has temperature and obeys the rules of warm things, then it must also have something physicists call entropy, a measure of how much information, how many possible internal arrangements it contains. For ordinary objects, entropy grows with volume. A bigger box can hold more arrangements of atoms. A bigger room can hold more possible configurations of furniture. But a black hole is different. The entropy of a black hole, the math shows, grows with the area of its event horizon, not the volume inside, the two-dimensional surface around it. This is a strange, beautiful fact. It suggests that everything happening inside a black hole, every detail, every memory, every scrap of fallen information, is somehow encoded not in the three-dimensional space within, but on the two-dimensional skin at its boundary. Some physicists have wondered whether the same might be true of the entire universe, whether all of reality is a kind of great hologram, three-dimensional life, written on a two-dimensional sheet at the edge of everything. The black hole, in this strange way, may be the universe's way of teaching us how it works. We just glimpsed it briefly, but it is worth pausing on. The entropy of a black hole, a measure of all its possible inner arrangements, depends only on the size of its surface. This was a discovery so surprising when it first appeared in the 1970s that it took years for people to take it seriously. Entropy was supposed to scale with volume, with how much three-dimensional space something occupied. Instead, in this one peculiar case, it scaled only with two-dimensional area. To this day, no one has fully explained why. The pattern hints that something about how nature stores information may not work the way we have always assumed, that the world has fewer degrees of freedom than we thought, that somewhere, at some level, three-dimensional reality may be a kind of projection. The clue is small. The implications are not. If a black hole is a place from which nothing can escape, then there is a natural opposite to imagine. A white hole, a place from which everything escapes, where matter pours outward, but nothing can ever enter. The math of general relativity allows white holes to exist. The same equations that describe a black hole can be flipped in time, and out comes the white hole, a strange object that vomits out its contents and refuses anything new. But here is the trouble. We have never seen one, not a single one in any corner of the sky. It may be that white holes simply cannot form in our universe, or that they exist for only an instant before something destabilizes them, or that they exist somewhere we cannot reach. For now, the white hole remains a mathematical possibility, a theoretical mirror of every black hole drawn in the equations missing from the cosmos. Sometimes, when physicists turn the equations of general relativity in particular ways, something even stranger appears. A bridge. If you could connect a black hole to a white hole, feeding things into one and having them emerge from the other, you would create what is sometimes called a wormhole, a tunnel through the fabric of space-time itself, connecting two distant places by a shortcut. The first physicists to take this idea seriously were Einstein himself, working with his colleague Nathan Rosen in the 1930s. They called it an Einstein-Rosen bridge, a theoretical pathway allowed by the math, but probably impossible to use. The trouble is that ordinary wormholes in the equations would collapse the moment anything tried to pass through them. they would pinch shut faster than light could cross. For a wormhole to be stable enough to use, it would require a kind of matter that has never been observed in nature. Some form of negative energy, something that pushes space-time open instead of letting it close. We have never found such matter. We have never seen a wormhole. They remain a beautiful possibility, a doorway hidden in the equations, waiting for a key we have not yet found. A spinning black hole holds a kind of stored energy in its rotation. In the 1960s, the British physicist Roger Penrose realized this energy could, in principle, be extracted. If you sent an object into the spinning region just outside the event horizon and broke it apart at exactly the right moment, one piece could fall in while the other escaped, carrying away more energy than the whole object had on the way in. This is called the Penrose process, a way of stealing energy from a black hole's spin, a trick of geometry hidden in the dance. The region where the Penrose process happens has a name. It is called the ergosphere, and it is one of the strangest places in the universe. The ergosphere is a layer just outside the event horizon of a spinning black hole. Inside it, the black hole's rotation drags spacetime itself along, faster than light moves. Anything entering this region, a ship, a star, a beam of light, is forced to rotate with the black hole. Standing still, in the ordinary sense, becomes impossible. But the ergosphere is not the event horizon. You can still escape from it if you have enough power. You can still leave with whatever energy you've gathered. It is the only place in nature where space itself is in motion, dragging everything within along with it. A river of geometry, flowing around the dark. We end this part of the night with one of the strangest ideas in modern physics. Some physicists have proposed that the inside of every black hole, past the event horizon, beyond all possibility of seeing, may contain something almost too large to hold in the mind, a universe of its own. The argument goes like this. The math of general relativity, applied to a collapsing object, predicts a singularity at the center. But certain extensions of the math suggest the singularity may not be a true endpoint. Instead, the collapse could rebound, continuing on the other side of the horizon, blossoming outward into a new region of space-time. That new region, viewed from the inside, would look like its own universe, its own space, its own time, its own history, ticking forward. If true, this would mean that every black hole is a kind of seed, that our own universe, which began in a hot, dense moment 13 billion years ago, may itself be the inside of a black hole, sitting somewhere in a larger cosmos we cannot see. It is a speculation. It may be wrong, but it is the kind of thought that black holes invite, a reminder that the deepest things may be deeper than we can imagine. There is a quiet hope that physicists hold about black holes, not yet proved, but deeply believed. It is called cosmic censorship. The idea is this: the singularity at the center of a black hole, where the laws of physics fail, is always, under all natural conditions, hidden behind an event horizon. The universe never lets us see it directly. The strangest places, the broken places, are always shielded from view. Without cosmic censorship, the universe would be deeply unpredictable. Singularities, naked to the cosmos, could do almost anything. Physics, beyond a certain point, would simply fail to apply. So far, the universe seems to have been kind. Every singularity we know of, or suspect, sits politely behind an event horizon, hidden from sight. We do not know why, but we are grateful. Earlier in the night, we touched on what it would feel like to fall toward a black hole. From your own view, your clock kept ticking. But from far away, the story was different. From the outside, your clock would slow. The closer you got to the event horizon, the slower your clock would seem to tick. Time, as measured by distant observers, would stretch and stretch. The light reaching them from you would redden, fade, and finally still. By the moment you appeared to actually cross the edge, measured from outside, your clock would have, by their reckoning, stopped completely. In a mathematical sense, no falling object ever finishes crossing the event horizon when viewed from far away. They slow asymptotically, frozen forever, fading into faint red ghosts at the edge of the dark. The fall itself, from outside, takes forever to complete. A rotating black hole has more than one boundary. The event horizon is the inner one. Inside it, nothing escapes, the familiar place of no return. Outside it sits another, called the static limit. Beyond the static limit, you can still move freely, but inside it, you cannot stand still relative to the distant stars. The black hole's rotation drags space-time itself, forcing you to turn with it whether you want to or not. The thin region between these two boundaries is the ergosphere, the place where the Penrose process happens, where space itself is in motion. So, for a spinning black hole, there is not just one edge, but several. An inner edge for matter, an outer edge for space-time, both circling the same dark center, in slow rotation. A black hole, when it spins, has layers. Black holes, the equations show, come in different mathematical kinds. The simplest is called the Schwarzschild black hole, the kind described by Karl Schwarzschild in his trench-side calculations during the First World War. A Schwarzschild black hole does not spin. It has no electric charge. It is perfectly spherical, perfectly still, a clean point of mass at the center, surrounded by a perfectly round event horizon. In nature, no real black hole is exactly like this. Almost every actual black hole spins. Almost every one carries some asymmetry. But the Schwarzschild black hole is the ideal version, the simplest possible black hole, the one used in classrooms, the one against which all the others are measured. A perfect mathematical sphere of darkness, exactly the way Schwarzschild first imagined it. In 1963, almost half a century after Schwarzschild, a New Zealand physicist named Roy Kerr finally solved Einstein's equations for a spinning black hole. It had taken decades. The Kerr solution describes a black hole that rotates, and once you allow rotation, almost everything about the geometry becomes more complicated. The event horizon is no longer a simple sphere. The singularity is no longer a single point. The space around the black hole is dragged along with its spin, faster nearer the edge. Real black holes in the actual universe are nearly all Kerr black holes. The Schwarzschild version is the simple textbook case. The Kerr version is what nature actually builds. A Kerr black hole, in its slow rotation, drags space-time itself like water in a vortex. Even an empty region of nothing spins with it. It is what real darkness looks like in motion. We have, in a way, come to the end of the story. But the story of black holes does not really end with their formation, or with their feeding, or with their merging. It ends, eventually, with their disappearance. A stellar mass black hole, evaporating slowly through Hawking radiation, would take 10 to the power of 67 years to fully fade away. That number is hard to grasp. It is one followed by 67 zeros. The universe itself is only about 13 billion years old, which is 14 zeros if you write it out fully. A stellar mass black hole would take a number of years far larger than the entire age of the universe, multiplied by itself 4 times over. These objects live, in a real sense, far longer than the universe has so far. From their point of view, we are sitting at the very beginning of time. Their lifetimes have only just begun. By the time the smallest black holes finally evaporate, every star will have long since burned out. Every galaxy will have grown dim. The universe will be a dark, empty place. The largest black holes live far longer still. A supermassive black hole, with the mass of a few billion suns, would take 10 to the power of 100 years to evaporate. 1 followed by 100 zeros. There's no name in any human language for that number. It is so far beyond ordinary counting that there is no way to picture it. Even saying it slowly takes a moment, a Google of years. If you imagined the lifetime of our universe so far as a single drop of water, the lifetime of a supermassive black hole would be larger than every ocean, every river, every drop of moisture in every cloud, on every planet, in every galaxy that has ever existed, multiplied together many times over. These are the most patient objects in nature. Their evaporation will outlast every other thing. Stars will die, galaxies will fade, even atoms themselves may decay. And yet the supermassive of black holes will still be there, slowly losing mass, fading by the smallest possible amount per year. A black hole's evaporation is not steady throughout its life. For most of its lifetime, the black hole leaks energy so slowly that the loss is almost meaningless. Less than a single particle's worth of mass per year. A whisper in a process measured against eternity. But near the very end, the rate accelerates. As a black hole grows smaller, it grows hotter. It radiates more and more energy. The smaller it becomes, the faster it shrinks. In its final moments, a black hole flashes outward in a burst of light and particles, a small explosion marking the end. After 10 to the 67th or 100 years of steady loss, the last few seconds are bright. A black hole goes out after all that long, dark life with a final flicker of fire. We are, by cosmic standards, very early in the history of everything. The universe is 13 billion years old. The stars are still burning. New stars are still forming. Planets, like our own, still orbit them. Galaxies still gather into clusters. The cosmos is full of light, but all of this will end. In a few 100 billion years, the last of the small, slow-burning red dwarf stars will run out of fuel. After that, no new stars will form. The galaxies will grow dim. The night sky, if there were anyone left to look, would gradually empty of light. The black holes by then will still be there. They will be the only thing left, slowly evaporating, drifting through enormous empty distances, the last bright objects in a fading universe. For a length of time we have no words for, the universe will belong to them. The story of the cosmos in the deepest future is their story. Cosmologists have a name for this far future stretch of time. They call it the black hole era. It begins when the last star has gone out and ends when the last black hole has evaporated. In between, perhaps for 10 to the 100 years, the universe is filled with nothing but the dark forms of black holes and the faint escaping particles of their evaporation. There is no light to speak of, no heat, no motion of any importance. The universe will be cold and dark and slowly fading. The galaxies will have long since broken apart. The atoms left will be alone, separated by enormous distances no eye will ever see. This is the age of black holes, the longest age of all, and it has not even begun yet. Long before the black hole era arrives, the supermassive black holes themselves will go through changes. When two galaxies collide, as the Milky Way and Andromeda will in a few billion years, the supermassive black holes at their cores do not collide directly. They orbit each other instead, slowly spiraling inward. The process takes a very long time. Tens of millions, sometimes hundreds of millions of years. The two black holes circle, gradually drawing closer, losing energy through the gravitational waves they send out into the cosmos. Eventually, they meet. The two giant black holes merge into one, even larger than before. Their combined mass slips into a single dark region, settling toward a new event horizon. Across the universe, this is happening all the time. Mergers of galaxies. Mergers of the dark hearts they each contained. Sometimes, when two black holes finally merge, the resulting object does not simply sit at the center of its new galaxy. The collision can be uneven. The merging black holes may have had different masses, different spins, different angles of approach. When they finally combine, the new black hole can be flung sideways by the asymmetry, pushed away from the galaxy's center at speeds of millions of kilometers per hour. Astronomers call these wandering black holes, or sometimes recoiling black holes. Giants kicked out of their homes by the violence of their own birth. Some of them are flung so hard that they leave their galaxy entirely. They become rogues, dark wanderers, traveling alone through the empty space between galaxies, no longer bound to any particular place. A black hole, sailing through the cosmic dark with no destination at all. Even our own galaxy, the Milky Way, is full of these wanderers. Astronomers estimate that the Milky Way contains around 100 million stellar mass black holes. Almost none are detected. They have no companion stars feeding them. They give off no X-rays. They do not announce themselves in any way. They simply move. Through the disk of the galaxy, through its halo, through the spaces between the spiral arms. Some are alone. Some are paired with dim, dead stars. Some pass close to ordinary stars without disturbing them noticeably. Right now, as you lie there, dozens of black holes might be quietly traveling through the region of space around our solar system. Far enough away to be unseen. Close enough on cosmic scales to be considered our neighbors. The Milky Way looks like a clear field of stars when we look up at it. But beneath that bright surface lies another galaxy. A dark population moving through the dust and the light, hidden in plain sight. Across all of cosmic history, black holes have been merging. Every collision, every coupling has sent gravitational waves rippling outward into space-time. Some loud and brief, like the merger of two stellar mass black holes. Some long and slow, like the dance of two supermassive giants over millions of years. Most of these signals are far too distant to be detected directly. But altogether, they form something physicists call the gravitational wave background. A faint, constant murmur of rippling space-time filling the universe. It is everywhere. It has been there for billions of years. It is the cumulative whisper of every black hole merger that has ever happened, anywhere in the cosmos. A low hum beneath the structure of reality itself. Earlier in the night, we spoke of quasars, supermassive black holes feeding so brightly that they outshine entire galaxies. The first one ever recognized was called 3C273. It was discovered in the 1960s in a survey of strange radio sources. At first, no one understood what it was. It looked like a star, but it sat at a strange distance, over 2 billion light-years away, and shone with the brightness of trillions of suns. 3C273 is, in fact, a supermassive black hole feeding rapidly on a stream of falling matter. Its accretion disk burns so brightly that, even at that distance, you could, in principle, see it with a backyard telescope. It is the brightest, closest quasar in our sky, a supermassive heart eating its way through the dark. Its light, traveling for 2 billion years to reach us, was already old when our planet was new. Since the first detection in 2015, gravitational wave observatories have grown more sensitive every year. LIGO has been joined by other observatories: Virgo in Italy, Kagra in Japan. Together, they listen to the sky for the soft tremors of distant cosmic events. Most of what they hear are black hole mergers. 2 black holes spiraling into each other somewhere far away, sometimes billions of light years from us. The waves they send out reach our instruments thousands or millions or billions of years later, faint by the time they arrive, but unmistakable. Each detection is a story. 2 dark objects born from dying stars, spending their lives in long orbits, finally meeting and joining. The signal we read on Earth tells us their masses, their spins, the size of the black hole they became. We are, for the first time in human history, listening to a part of the universe we could not see. Not the light of stars, not the warmth of nebulas, the sound of space-time itself ringing, a subtle new sense, astronomy by ear. In the deepest future, even the largest black holes will be gone. The supermassive black holes will be the last to evaporate, because their lifetimes are so absurdly long. But they will eventually fade. Particle by particle, photon by photon, the energy that defined them will leak back into the surrounding space. The horizon will shrink. The mass will diminish. And finally, like a candle burning out, even the largest of them will give a final flash and vanish. What remains when the very last black hole is gone? A universe of unimaginable emptiness. Cold beyond cold. Dark beyond dark. Containing only the faintest particles, scattered so far apart that any meaningful interaction between them is essentially impossible. Photons drifting alone, separated by distances no force can bridge. The universe will not end with fire. It will not end with ice. It will simply thin out until everything that ever happened is too far apart to ever happen again. That is the deepest future. The slow undoing of everything. The cooling of a cosmos that once burned so bright. It is worth pausing for a moment to take in what we have walked through. We started in the dark, watching someone fall toward a black hole, their motion slowing, their light reddening, their image fading at the edge of nothing. Since then, we have wandered through ideas as far apart as the marble-sized horizon of a planet-mass black hole, and the 100 billion sun heart of an ultramassive giant. We have seen our own galaxy's still center, and the first photograph of a black hole ever taken. We have followed Stephen Hawking's careful math to the discovery that black holes glow. We have watched mergers ripple across space-time. We have peered into the deep future when nothing will be left but the slow evaporation of darkness itself. And through all of it, the most strange and beautiful thing is this. Black holes are not only endings, they are also beginnings. The bright disks around them shape new stars. The collisions between them carry energy across the cosmos. Their evaporation seeds the late universe with the last warm particles it will ever know. In the long story of the universe, Black holes are the dark threads holding the rest together. Tonight, you do not need to remember any of it. You only need to rest. In the deep, deep future, after every star has burned out, after every galaxy has dimmed, after even the longest-lived black holes have nearly evaporated, the universe will hold only the faintest traces of structure. The black holes will be the last shapes still recognizable, slowly fading, slowly going dim. For a span of time so long it makes ordinary numbers feel meaningless, this is what the cosmos will be. Empty regions, unimaginably wide. A few black holes, here and there, slowly losing the last of their mass. Nothing else of any real substance. And then, eventually, even those last black holes will fade. When the final supermassive black hole gives off its last flicker of Hawking radiation and vanishes, there will be no more structure in the universe. No black holes, no stars, no planets, no atoms still bound together. Just particles, scattered across distances no light could ever cross. The universe, after the black holes are gone, will be the simplest it has ever been, or the simplest it ever will be. Every black hole that has ever existed, every one we have observed, every one we have only imagined, every one in every distant galaxy, will, in the end, dissolve. Born violently, in the death of a star or the chaos of an early universe collapse, living patiently, sometimes for billions, sometimes for unimaginable trillions of years, feeding, merging, growing, fading. And finally, when its time comes, evaporating into the silence from which it came. This is the long arc of every black hole. The same long arc, from a tiny stellar mass black hole to the largest ultramassive giants. Different scales, the same story. Stars give birth to them. The universe holds them for a time. The slow physics of evaporation takes them away. And so, in the end, the strangest objects in the cosmos are not eternal. They are patient. They are dark. They are deep beyond what we can imagine. But they too, like everything else, eventually return to the dark between the stars. A long, gentle ending for the strangest things the universe ever made. And now the stars begin to fade behind your thoughts. We have wandered tonight through one of the strangest places in the universe, through the dark sphere photographed at the heart of M87, through the giant at the center of our own galaxy, through the long, slow fall toward an event horizon and the deeper fall beyond. We have followed black holes through their birth, their feeding, their mergers, and their slow disappearance. We have stood at the edge of questions no one yet knows how to answer. We have watched a star become a singularity, a galaxy build a giant evaporate into nothing across an unimaginable span of time. You do not need to hold on to any of it. The black holes will still be there in the morning. They will still be turning slowly in distant galaxies. They will still be drifting, unseen, through the corners of our own. They will still be patient, as they have always been. If anything you heard tonight stays with you, let it be the small comfort of knowing that even the deepest, strangest things in the universe move on their own time. They are in no hurry. They have all the time there is. Let the room around you grow still. Let your thoughts drift. Let your breathing slow. Sleep well. Dream softly. Good night.